Hello students, welcome you all. Now in this lecture I will tell you the correlation diagrams for the electrocyclic reaction. So in my last lecture I told you about the conrotation, disrotation, these two terms, and the selection rule for the electrocyclic reaction. So the selection rule, it can be analyzed by the various ways. One of the way is by the correlation diagram or conservation of orbital symmetry correlation method. So in my first lecture of this pericyclic reaction, I told you the pericyclic reactions, they may be analyzed in various ways. One of the way, that is orbital symmetry correlation method, that is by using the correlation diagram. Second, by the frontier molecular orbital method, and third, by the Huckel-Mobius method. So let's analyze the selection rule for this electrocyclic reaction with the help of this correlation diagram. So in my last lecture, what I told you, the selection rule for this electrocyclic reaction. So this was the selection rule. So suppose, two type of systems we will analyze. One is the 4n electron system and another is the 4n plus 2 pi electron system or 4n plus 2 electron system. So 4n electron system under thermal condition. In 4n electron system under thermal condition, the orbitals will undergo conrotatory motion, whereas under photochemical conditions the movement of orbital will as the disrotatory motion. They will follow the disrotatory motion. For 4n plus 2 electron system, the 4n plus 2 electron system under thermal condition, disrotation of molecular orbital will occur, and under photochemical condition, conrotation of this orbital will take place. So this is our selection rule for this electrocyclic reaction. Now this selection rule that we can analyze with the help of this correlation diagram. So what is this correlation diagram? So what I told you in the pericyclic reactions, the reactant orbital and the product orbital, they have the same symmetry. They should have always the same symmetry. So in correlation diagram, reactant orbital and product orbitals having the same symmetry are joined with the help of line. So what is this correlation diagram? The reactant orbital and product orbital having the same symmetry are joined with the help of straight line. So reactant orbitals and product orbitals having same symmetry is joined with the help of a straight line. So this is the correlation diagram. Okay. So same symmetry molecular orbitals are correlated, are joined with the help of a straight line. So two type of systems, one is the 4n electron system and 4n plus 2 electron system. In 4n electron system, the orbital may undergo conrotation or it may undergo disrotation. So conrotation will occur under the thermal condition, disrotation will occur under the photochemical condition, and similarly for 4n plus 2 electron system. So first of all, we will analyze the 4n electron system. So first of all, let's see 4n electron systems. First of all, we will see the 4n electron system. So in 4n electron system, what we can, I have told you, suppose I take the example of simplest 4n electron system. So cyclobutene. Cyclobutene, it may under either thermal condition or photochemical condition, that would be converted into butadiene. Okay, so under thermal condition or photochemical condition, that would be converted into butadiene. So during this reaction, so this reaction may occur either by the conrotation of orbital or disrotation of orbital. Now, so what are the molecular orbitals which are involved during this reaction? So if you will see here, so this will go here and this will go here and this will form the butadiene system. So how many electrons are involved in this reaction? In this reaction, 4 electrons are involved in this reaction. So 2 electrons of this sigma bond and this 2 electron of this pi bond, they are involved in a cyclic rotation, cyclic shift of electrons. So cyclic shift of electrons of this sigma electrons are involved, and this pi electrons are involved. So corresponding to this sigma orbital, so the molecular orbitals would be, what are the molecular orbitals involved corresponding to this sigma orbital? So molecular orbitals involved are sigma, sigma star, pi and pi star. So in reactant, that is in cyclobutene, these 4 molecular orbitals are involved in the reaction. In product, this is a butadiene. So what are the molecular orbitals which are involved in this product? In product, no doubt, all molecular orbitals of the butadiene, and we have seen the construction of molecular orbital for the butadiene. So we can assign this 4 molecular orbital as psi1, psi2, psi3 star and psi4 star. So these molecular orbitals are involved in the product. So these are the product molecular orbitals, these are the reactant molecular orbital. Okay, so now we can draw the molecular orbital of this at one side, and at other side we will draw the molecular orbital for this product. So let's see. So first of all, suppose this is sigma molecular orbital, and suppose I write one of the line in the middle, and suppose this is the product molecular orbital, and this is sigma star molecular orbital. Okay, sigma, it is the strongest bond in comparison to pi. It is the strongest bond. That's why strongest bond means most stable. So that's why out of this 4 molecular orbital, sigma will be the lowest energy molecular orbital, most stable one. Sigma star, weakest one. So that's why it is the highest energy molecular orbital, or it is the least stable molecular orbital out of this 4. So out of this 4, most stable is the sigma molecular orbital, least stable is the sigma star molecular orbital. Now out of this pi and pi star, so pi, I will draw this pi over here. This is the pi. No doubt this pi molecular orbital will always have the higher energy, higher than the sigma molecular orbital, and this would be the pi star molecular orbital. This would be the pi star molecular orbital. Okay. So these 4 molecular orbitals, this is of cyclobutene. This is of cyclobutene. Now this cyclobutene, this would be converted into cyclobutadiene system. So this may undergo either the conversion of this cyclobutene into butadiene. This may take place either by disrotation of orbitals or the conrotation of orbital. So I will first take the disrotation. And in disrotation, according to this selection rule, the disrotation of orbital occur in a photochemical condition. So this we have to analyze. So we are analyzing this selection rule with the help of this orbital symmetry correlation method, or in which we draw the correlation diagram. So here, we are first analyzing disrotatory motion or disrotation. We are analyzing first the disrotation. Okay, so these are the molecular orbital of reactant. Now let's draw the molecular orbital of this product, that is butadiene. Now where we should draw the molecular orbital of this butadiene? So psi1, where I should draw the psi1? At which energy level the psi1 should be drawn? I will draw the psi1 over here. This is psi1, and this I am drawing this psi2 over here. This is psi2, and this is psi3 star, and this is our psi4 star. Okay. Now, why I have drawn this psi1 above sigma, or we can say why I have drawn psi1 below pi, why I have drawn psi2 below this pi, why I have drawn this psi3 star below pi star. So this can be understood. This can be understood with the help of this overall energy. So what we can say, the energy level, the energy of this psi1 is less than pi, energy of psi2 is greater than pi, and so on. So this can be understood with the help of interactions, bonding and anti-bonding interaction. More is the bonding interaction, more will be the stability. More is the anti-bonding interaction, lesser will be the stability. So if you will see, then in this case for butadiene system, if you will see the bonding interaction in butadiene, so in psi1, all signs are positive for this psi1. So number of bonding interaction, as I have already told in my previous lecture of the construction of molecular orbital diagram for butadiene. So for this, the bonding interaction is 3, and this for 2, this has 1 bonding interaction, this has 0 bonding interaction. So if you will see the sigma, how many bonding interaction are there in sigma? So this is the sigma. So this is your sigma, and in sigma you will see 1 bonding interaction is there. In sigma you will see 1 bonding interaction. In sigma star, so this is the sigma star, this is the sigma star plus, this is minus, this is minus, this is plus. So here the 0 bonding interaction, whereas there 1 anti-bonding interaction. Okay, and if you see the anti-bonding interaction, then here anti-bonding interaction will be 3, here 2, here 1, and here 0. And here if you will see the anti-bonding interaction is 1. So this is, here the anti-bonding interaction is 0, anti-bonding interaction. Now what about this pi? This is your pi. This is pi plus plus minus minus. For this bonding interaction, 1 bonding interaction. Pi star bonding interaction is 0, whereas in pi number of anti-bonding interaction is 0, and the anti-bonding interaction in case of pi star, so this is the pi star, this is the pi star, plus minus. So anti-bonding interaction is 1. Okay, so like this, and this I have written the bonding interaction, this I have written the anti-bonding interaction, like this. So if you will see why I have drawn the energy level like this. So what I have told you, we can understand it with the help of this total bonding or total anti-bonding interaction. So if you will see here, then psi1, no doubt this is pi molecular orbital. That's why this pi molecular orbital will always have the energy higher than the sigma molecular orbital. That's why this psi1 has the higher energy than the sigma. And otherwise, if you will see, and if you will compare this psi1 with this pi, then pi having the 1 bonding interaction and psi1 is having the 3 bonding interaction. It means this is more stable, that's why of lower energy. Psi2 is having the 2 bonding interaction, whereas pi is having the only 1 bonding interaction. So that's why it has the high. Otherwise, 2 bonding interaction is there, but also it has 1 anti-bonding interaction. 2 bonding and 1 anti-bonding. So overall it will cancel and you will left with only 1 bonding interaction. So we can say that here for Psi2, effectively there is only 1 bonding interaction. Okay, because there 1 anti-bonding interaction is present, that's why bonding out of 2 bonding and 1 anti-bonding, we are left with 1 bonding interaction. Here only 1 bonding interaction, there is no anti-bonding interaction. That's why, since here no anti-bonding interaction is there, that's why this should be of lower energy, this should be of higher energy. So anti-bonding interaction leads to the higher energy. So since 1 anti-bonding interaction is present over here, that's why it should be of higher energy. In the same way, we can explain the energy of this and this. If you will see, then Psi3 star is having the lower energy, pi star is having the higher energy. Why? Because here overall, if you will see, there is 1 anti-bonding interaction, and here if you will see, here also 1 anti-bonding interaction. Here 1 anti-bonding interaction, 1 anti-bonding interaction, but it has 1 bonding interaction also. Okay, overall if you will see 1 bonding, 2 anti-bonding, if you will cancel, then we are left with 1 anti-bonding interaction, but it is having the 1 bonding interaction also. That's why here there is no bonding interaction, that's why it is having the lower energy, and like this. So if you will compare this one and this one, if you will compare this one pi star and Psi4 star, then this is having the 3 anti-bonding interaction and this is having the 1 anti-bonding interaction. That's why no doubt it will have the higher energy. So like this we can understand the energy level for this one. We may understand the energy level, and now let's see how we can join these lines. So now during disrotation, what I told you in my previous lecture, during disrotation which symmetry is maintained? Mirror plane symmetry is maintained. So sigma is maintained here. Sigma is maintained in mirror plane symmetry. Sigma is maintained. So like if you will see my previous lecture, then you will see that Psi1, what I told you, Psi1, all signs are positive, and if we pass a mirror plane from the middle, then this is symmetric with respect to the mirror plane. So mirror plane, M stands for mirror plane, and this is symmetric with respect to the mirror plane. Psi2, half orbitals are positive, half orbitals are negative. If we pass a mirror plane in the middle, then what you will find, it is anti-symmetric with respect to the mirror plane. In the same way, what I told you, SA, like this, that in this way you can remember the things. So this will be symmetric with respect to the mirror plane, and this is anti-symmetric with respect to the mirror plane. Okay, now let's see for this one. For this, this is sigma. Sigma, if you will see, then this is symmetric with respect to mirror plane. What was the sigma? This is the sigma. This is plus, 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 plus. If you pass the mirror in the middle, then what you will find, this is symmetric with respect to the mirror plane. This is symmetric with respect to mirror plane. If you will see pi, then this is also symmetric with respect to mirror plane. This is also symmetric with respect to mirror plane. And psi star, pi star, it means this will be minus, this would be plus. So if you will pass mirror plane, then it is anti-symmetric with respect to the mirror plane. And sigma star, one plus, another minus, and this will be plus. So this is also anti-symmetric with respect to the mirror plane. So during this rotation we are only concerned with the sigma. We are not concerned with the C2, we are only concerned with the sigma. So what we have to do in the correlation diagram, reactant orbital and product orbitals having the same symmetry are joined with the help of a straight line. So which are having the same symmetry? This is the reactant molecular orbital, this is the product molecular orbital. Let's join it with the help of a straight line having the same symmetry. So same symmetry, this is sigma, mirror plane symmetric, and this is also mirror plane symmetric. So this is psi 3 star is also mirror plane symmetric, but out of this psi 1 and psi 3 star, psi 1 is having the lower energy, that's why we will join it with this line. Now if you see again pi, so pi that should be correlated with, because this pi is symmetric with respect to mirror plane, we will correlate with the symmetric molecular orbital only. So in product, only the psi 3 star is symmetric with respect to mirror plane, that's why I should join like this. Now pi star is antisymmetric with respect to mirror plane, so I should join with antisymmetric in the product molecular orbital. So in product, this is antisymmetric, this is also antisymmetric, but since this is of lower energy, so this is of lower energy, that's why this would be more energetically favorable. And this sigma star is antisymmetric, and now the only left is this antisymmetric, I should join like this. Okay, so this is the simple diagram, this correlation diagram for the 4n electron system which is involved in the disrotatory motion of the orbital. Now during this rotation, what we have seen in this selection rule, during this rotation this is only allowed under the photochemical condition. So we will see that this would be allowed in the photochemical condition only. So let's see, let's prove that during this rotation only it is allowed, this rotation is only allowed under the photochemical condition, that I will prove here. So how we can prove here? So if you will see, then the 2 electrons, how many electrons are involved in this reaction? 2 electrons are involved. 4 electrons in butadiene, or this 4 electrons in cyclobutene. So 4 electrons are involved, so I should fill the molecular orbital, 4 electrons that should be filled in the molecular orbital. So 2 electrons over here and 2 electrons over here. Okay, now so let's see. So when the under thermal condition, under or photochemical condition, what happens? This electrons, they are going into the, they are transferred to the, this converted into the this psi 1 molecular orbital of the product. So 2 electrons are going into psi 1 and these 2 electrons are going into psi 3 star. So under thermal condition, if you will see, so let's see for thermal condition. Under thermal condition, first one is under thermal condition when 2 electrons are present in the ground state. So in sigma 2 electrons are present, in pi 2 electrons are present. Okay, in sigma 2 electrons, in pi 2 electrons. So when this rotation, during this rotation, what you can see, these 2 electrons are going into psi 1 and these 2 electrons are going into psi 3 star. Psi 3 star. Now if you will see, then this is the lower energy ground state and these are the excited state, and out of this is the first excited state, this is the second excited state. We also may call it a higher energy excited state. So this is first excited state, this is higher energy excited state. So and these are the ground state. So this sigma and pi, they are the ground state, whereas psi 1 square and psi 3 star 2, this is our first excited state. Psi 3 is the first excited state. So electrons, the transfer of electron from ground state to the first excited state is not a favorable one. So this is not favored because the transfer of electron from one energy, from one energy level, they may transfer from in a same energy level. So the transfer of electron from one energy to the higher energy level is not energetically favored. So that's why this process is disfavored. This process is disfavored. Now if you will see the second, that is under photochemical condition. Under photochemical condition. So under photochemical condition, one of the electron from here, that would be transferred to the higher energy level here. So under photochemical condition, after absorbing the light, this electron will go over here, it will get excited to this one. Means it has gone to the first excited state. Now what you can see, from here electron is going into here, and from here this pi electron, one pi electron is going into psi 3 star, pi star electron is going into psi 2. So what I should write here, sigma 2 electrons are present, in pi 1 electron is present, in pi star 1 electron is present. Now this sigma electron is going into psi 1, pi electron is going into psi 3 star, okay, where pi star electron is going into psi 2, pi star electron is going into psi 2. So this is our first excited state, and this is psi 3 electron is going into psi 3 star. This is also first excited state. So from first excited state to first excited state, so this process is energetically favored. So this process is energetically favored. So this is disfavored and this is favored process. So same thing I have written in the selection rule. So this analysis, like this we can analyze. So for 4n plus 2 electron system, what you have seen, this 4n plus 2 electron system, when the orbitals undergo disrotation, so orbitals, the disrotation movement of rotation of orbital is only possible under the photochemical condition. Under thermal condition, the disrotation is not possible. Under thermal condition, only conrotation is possible. Let's draw the orbitals, this correlation diagram when orbitals undergo the conrotation. Okay, so let's see when orbitals undergo conrotation. So conrotation of orbital. Okay. Now, so during conrotation, which symmetry is maintained? So here also I should write the conrotation, and for conrotation I have already explained, in conrotation only C2 is maintained. C2 symmetry is maintained during the conrotation of molecular orbital. So as you can see, this psi 1, all are positive, all sign of the lobes are positive. So psi 1, I have already given that psi 1, the C2 is asymmetric with respect to psi 1. So this was the psi 1, this is the psi 1 plus 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 plus, like this. So this is psi 1 and this is asymmetric with respect to C2. So if you will pass a mirror plane, if you will pass the axis of rotation and if you will rotate it by 180 degree, then what you will find after rotation, this you will not find the same molecular orbital. So because after rotation this point will go over here and this will go over here. In the same way, this negative charge will come at the place of positive charge, and this negative charge will go at this positive charge place. So we will not get the same molecular orbital after the rotation by 180 degree. That's why it is antisymmetric with respect to the mirror plane. Whereas if you see psi 2, this is our psi 2, this is negative, positive, positive. So what about this? This is symmetric with respect to psi 2, C2. This is symmetric, psi 2 is symmetric with respect to C2. Why? Because if you will rotate it by 180 degree, what you will find? So this plus will go at this plus place, this minus will go over here at this minus. So you will get the same molecular orbital after rotation at the angle of 180 degree. So that's why the C2 is symmetric. In the same way, this psi 3 star is asymmetric, and psi 4 star, that would be symmetric with respect to C2. So during conrotation, only C2 is maintained in reactant and product. So here, if you will see here, then sigma. What about sigma? Sigma is whether symmetric with respect to C2 or not. So this is sigma. This is our sigma. Plus, plus, minus, minus. So if you will pass the rotation axis and if you rotate it by 180 degree, what you will find? You will find in place of minus, minus will come, in place of plus, plus will come. So if you rotate it by 180 degree, in place of minus, minus will come, in place of plus, plus will come. You will get the same molecular orbital after rotation through 180 degree. So that's why it is symmetric with respect to C2. It is symmetric with respect to C2. Whereas if you will see sigma star, this is the sigma star. If you will rotate, then at this minus, plus will come, and at this plus, minus will come after rotation by 180 degree. That's why this is C2 is asymmetric with respect to this. What about pi? Pi is, if this is the pi, this is pi, plus, plus, minus, minus. So if you will rotate it by 180 degree, at plus, minus will come, and at minus, plus will come. That's why it is asymmetric with respect to C2. And this pi star, this is pi star, and this is, if you will rotate it by 180 degree, and what you will find? You will find that at plus, this plus will come, at this minus will come. So that's why this is symmetric with respect to C2, like this. So we have given the C2 symmetry, whether it is symmetric or not. We have given all sign to this molecular orbital. Now we can join this. We can join with the help of same symmetry molecular orbital in reactant and product. That should be joined with the straight line. So if you will see, then this sigma having the symmetric, C2 is symmetric in sigma, so that should be joined with the symmetric molecular orbital. So symmetric molecular orbital in product is, this is symmetric and this is symmetric. But this is of lower energy, that's why I should join like this. Now pi is antisymmetric with respect to C2. So we should join this pi with the product molecular orbital, which is antisymmetric. So you will see that this is antisymmetric, this is also antisymmetric, but this is of lower energy, this is of higher energy. That's why I should join like this. Now see this pi star. Pi star is symmetric, so I should join with the symmetric. Only left is that this is symmetric left, and this sigma star is antisymmetric. The antisymmetric left in the product is this one. So this is the diagram. This is the correlation diagram for the 4n electron system where the conrotation of molecular orbital takes place. So in 4n electron system, for conrotation, it takes place under the thermal condition only. You can see under thermal condition only the conrotation takes place. So let's see if you will now. So that's why first condition under thermal condition. Under thermal condition, if you will see, then 2 electrons are present over here and 2 electrons. Total 4 electrons are present, 2 here and 2 here. Okay, so this sigma electron is going into psi 2, pi electrons are going into psi 1. Sigma 2 electrons, and in pi we have 2 electrons. Sigma electrons are going into psi 2. Sigma electrons are going into psi 2. Pi electrons are going into psi 1. Pi electrons are going into psi 1. So you will see that this is ground state and this is also ground state. Ground state, ground state, both are ground state. So this is energetically favored. So this process is favored. This process is favored. Whereas if you see under photochemical condition, what you will see, under photochemical condition, one of the electron will get excited to this one. Now here pi star electron that is going into the pi 4 star electron. So what sigma contains the 2 electron, pi contains the 1 electron, okay, and pi star contains the 1 electron. Now sigma electron is going into psi 2, whereas pi electron is going into psi 1, whereas pi star electron is going into psi 4. Okay, like this. So if you will see, then this is the first energy excited state, but when electron is going into psi 4 star, then this is higher energy excited state, or it is the second energy excited state. So electrons are going from first energy excited state to the higher energy excited state. So this is first excited state, this is the higher energy excited state, which is not feasible. Okay, so electron can only go in the same energy states. So that's why this is disfavored, this is disfavored. So this is not possible. So what you have seen, and the conrotation for 4n electron system, when conrotation of orbitals occur, so this occur only under the thermal condition. In photochemical condition, this is not allowed. Okay, so this is the correlation diagram for 4n electron system. Now in my next lecture, I will tell you the correlation diagram for 4n plus 2 electron system, and we will analyze the rule for this 4n plus 2 electron systems. Okay, thank you.